Great. So my name is John, and this summer I was working with Dr. Lathrop. Whoops. And my project was the study of what we're calling the parametrically diagram on the right. This is a damped planar pendulum where the pivot is oscillating vertically, and we've added to make the dynamics a little bit more interesting. So the standard parametrically driven pendulum is the same system just without the magnet, and this is an early example of a simple mechanism that exhibited chaotic dynamics. And this chaos depends on several parameters, some of the most important being the driving amplitude, we've noted, and the relationship between the driving frequency and the natural frequency of grid. To model the addition of a magnet to the system and then explore the new dynamics. So when we add the magnet, we get these equations of motion, which are very nonlinear and a little bit ugly. Is that the addition of the magnet has taken what was previously an attracting fixed point in phase space at theta equals 0 and turned it into a saddle point. So you can see in this potential energy diagram here, we have a double well potential, which inspired the name of the system. And what's usually in a normal pendulum, a stable equilibrium at theta equals 0, so pendulum pointing down, is now an unstable equilibrium. And so to solve the equations of motion, we use numerical integration, specifically Runge-Kutta 7-8. And the following parameter values for everything is in MKS units. And the important thing to take away is that the driving frequency was twice the natural frequency. And our general pattern of investigation was to keep these parameters fixed and then vary our driving amplitude and see how that affected the dynamics. So really quickly, this is just a phase space plot with no driving and no friction to get a sense for what the system is like with the magnet. Technically, to fully specify the state of our system, we, in addition to the angular velocity and angle, would need the time or the phase of the forcing. So this is a 2D plot of phase space. And you can see, like I mentioned earlier, there's a saddle point at theta equals 0, so the pendulum pointing straight down, and then at theta equals plus or minus pi, where the pendulum is pointing straight up. And so when we add back driving and friction, we would expect the system to develop some kind of long-term behavior. So this is a plot of theta versus time for a pretty small driving amplitude with two different initial conditions. And we see that the emotion is initially very different, but after 40 or 50 seconds settles into some long-term behavior. Because this behavior is periodic, it makes a closed curve in phase space, and we call that curve an attractor because it attracts different trajectories onto it in phase space. And linear oscillators have a unique attractor, but as you can imagine, nonlinear systems, things get a little bit more interesting. And so we observe up to 10 coexisting attractors for a given driving amplitude. Pictured here is a phase space plot of 5 different attractors. And so the idea is no matter what your initial condition or where you start in phase space, eventually you'll end up on one of these attractors, and the specific attractor or trajectory that you end up on is dependent on the initial conditions. And so another way to view the dynamics of a system is with a Poincaré section, and we make a Poincaré section by starting with a trajectory in the full 3-dimensional phase space. So our third axis here is the cosine of the phase of the forcing. And we take a plane at cosine omega t equals 1 and find the points where our trajectory intersects with that plane. And then we plot those points on a theta dot versus theta graph. And this has the advantage of making it pretty easy to see what the period of our trajectories are. So for instance, here we have a period 4 orbit, meaning that the pendulum is repeating its motion every 4 drive periods. And it also has the advantage, as we'll see in a little bit, of being better suited for visualizing more complicated attractors. So we see that when we increase the driving amplitude a little bit from what it was in the previous phase space plot, we still have the same 5 attractors, although now they're being represented by points in the Poincaré section as opposed to curves in the full phase space. And we also now have a strange attractor. So a strange attractor, instead of being just a finite collection of points, is actually a kind of complicated fractal structure in the Poincaré section. And it's indicative of chaotic dynamics. So when the pendulum is moving along the strange attractor, its motion is actually chaotic. And so Poincaré sections and phase space plots are good for viewing the dynamics at a specific driving amplitude. But if we want to see how the dynamics of the pendulum change as we change the driving amplitude, we can use what's called a bifurcation diagram, where we take the theta dot value at each point on this Poincaré section and plot it against our driving amplitude. And when we do that for lots of driving amplitudes, we get a bifurcation diagram. We can see how the attractors evolve as we vary the A value. And you'll notice there are certain points where the nature of the attractor seems to abruptly change. These are called bifurcations. And there are lots of different kinds, but one important one for us is a period doubling bifurcation, where if you have a periodic orbit, as you increase the A value, the period abruptly doubles. And you can have lots of period doubling bifurcations in a row, where the period approaches infinity and the motion becomes chaotic. And this is called a period doubling cascade, and is actually the process that led to the strange attractor we saw in the previous Poincaré section. And because we had so many coexisting attractors, we actually saw a simultaneous period doubling cascade, which was kind of cool. And then for much larger driving amplitudes, we found sort of a large strange attractor. So you can see the Poincaré section here on the right. And the fractal nature of this attractor is a little bit more apparent. And we can actually calculate what's known as a fractal dimension for this attractor, which we estimated to be about 1.75. And very loosely and non-rigorously, the fractal dimension is a way of expressing the idea that in phase space, this attractor is taking up more space than just a one-dimensional line would, but less space than a two-dimensional surface. And so that's why we get a number between 1 and 2. We also plotted some basins of attraction for different driving amplitudes. And the idea with these is that each color represents the attractor that the initial condition ended up on. I'm unfortunately running out of time, but if this looks interesting, I would be happy to talk about this more during the poster session. And then just real quickly, I really want to thank Dan and everyone in his lab, as well as Daniel and everyone involved in Trend for putting on such a good program despite the difficult circumstances this summer. So thank you.